when the timer has advanced beyond time 2, it's time to switch keys for interpolation. So we've reached a new key. So key 1 is now going to be what key 2 was. So we're moving to the right along the timeline. And key 2 advances. And if key 2 is greater than or equal to the number of keys, then that means we've reached the end of that animation cycle, in which case we have to respond based on whether we're looping or not. If we're not looping, we need to stop the animation. So we'll stop key 2 at the last key on the timeline, which is number of keys minus 1. We'll say stopped is true, timer is 0, done animation is true. We'll update the last reverse status. Reverse should be false, so last reverse should be false. Oh, I don't know why this is time diff, it should be timer. So make sure to change that to timer. Otherwise, it's looping animation, and we need to loop it. Key 1 is 0, key 2 is 1, timer is 0, then animation is true. Just signaling that it reached the end of the cycle, and it's restarting. So this responds to when we reach the end of the animation cycle, loops it or stops it. T1 is at T2, let's just copy this, is the time for key 2. Okay, so let's copy all of this stuff here and make a version of it for reverse animation. So we'll paste it here. Alright, so this is going backwards. So we're going to say less than T1. And key 2 will now equal to key 1 because we're going in the reverse direction. Key 1 has to go backwards towards 0. And we'll say if key 1 is less than 0, and it's reached the beginning of the timeline. So for this version, this one might be a little more complicated. We're going to say, we'll change this. We'll say key 1 equals 0, key 2 equals 0, and stopped is true. And the timer is going to be meo.anim.a.times key 1. Since the animation stopped, if it ever does start it again, we're assuming that the default is going to play it in forward. So we've got to make sure that it's prepared for forward animation. Otherwise, we start it with the reverse version, where we say play backwards is true, in which case it'll call this start reverse and set it up for reverse. So we're kind of setting it up from going from reverse to going to forward. So timer is set to the time for key 1 and then return. Okay, otherwise we're going to say that key 1 is going to be num keys minus 2 because it's the one on the left side, whereas key 2 will be key 1 plus 1 because it's to the right. So this is technically num keys minus 1. Now timer, we want to reset it to be, because this is looping, the time at key 2, going from right to left. So we just update key 1, key 2, and then take the time based on the current keys. Same thing. Another thing too to keep in mind is sometimes I make customizations to the key 1 time for when it should start. So that's why I want to set the timer to be the actual time for key 1. In fact, it might actually be better to put this here for when you're starting your animations. In fact, I'm going to do that. Let's just start another line here because this looks crazy. This will have to be changed to animation index, and same here. Okay, I mean, chances are good your initial time, key 1, is going to be 0. So you could leave it as 0 if you wanted. Okay, let's get the time difference between the two keyframes used in interpolation. And we'll say if the time difference is less than or equal to 0, which should never happen. We'll just, to be safe, we'll make sure that it's 0. Some really small number. So we'll say the percent is where the timer currently is between T1 and T2 and T1. So timer minus T1. How far in is it? Divided by that total time difference. What is the percentage between T1 and T2 is what we're asking here. Okay, I just added some comments real quick. Vector 2, position, scale, offset 1, offset 2, offset 3, and offset 4. So this is where the fun stuff comes in, where we actually get to sort of model and animate how the quad is shape-shifted and rotated and scaled as the animation goes on. These are X coordinates. We'll do the same with Y. So we're going to loop, and we'll need index part. So we'll say I plus plus while I is less than the part count. So loop through all the parts for this animation and animate them. Just to be safe, we're going to say last reverse is equal to the current value of reverse. So we're going to keep track of whether the animation's in forward or reverse. That way, when we do an is animation done check, if the state has changed from forward to reverse or vice versa, it will return false because it's continuing the animation but in a different direction. And that's what the purpose of that is. First thing we'll do is in our final rendering data, we'll make sure we store the order that we want to render at. based on key 1 what the order is that it's supposed to draw things at. When it goes to render the final data, what it'll do is it'll loop with a index n from 0 to however many final things there are to render, and it'll get an index, and then it'll extract from that index, which is the order index, which final data to actually use. So it's using the final data in the correct order. Sounds a bit confusing, but it works. If meow.anim a. So if this keyframe is not active, then we can hide this part during this frame period by saying final.hide as true. And then we know we don't have to do any more processing for this final piece. So we advance our counter and continue the loop. So go back to do, because the part is not going to be shown anyway. Otherwise, we need to make sure hide is set to false. Okay, and let's make sure we get the actual part that's supposed to be rendered. During the timeline, that information can be altered in the animation editor. So you could swap parts, maybe use different hands or something. So we'll get the actual part that's supposed to be rendered. And to make things a little easier, we're going to set P to be that value. Let's begin by interpolating the data between the two keyframes for the animation. So final I.alpha, it's our final render data's alpha value, and we're going to use linear interpolation. I tried it with more advanced animation interpolation and didn't really make enough difference for anyone to notice. So linear interpolation is definitely good enough as far as I'm concerned. So the alpha value at key 1, and we're interpolating towards the alpha value at key 2 based on the percentage that we calculated up above. So that's what this was all about. We get the time difference between the two keyframes. We figure out what percentage it is between each keyframe. So 0.2 would be 20%, for example. If this was 0.2, it would be 80% at keyframe 1 and 20% at keyframe 2, because it's 20% of the value between this value and this value, starting and target. If you understand interpolations or worked with them before, this will be very familiar to you. So as an optimization, we're going to say if the value for the alpha is less than hide alpha under, then we can just hide it and we don't need to show any of it at all or do any more calculations, because you're not going to be able to see it anyway. And as a precaution, let's make sure, here I'm just going to pause this. If alpha is greater than 1, then we set alpha to be 1, just to make sure it doesn't go over that. So now we'll do an interpolation of the position for the part. Vector2, linear interpolation. The position value at key 1, just copy and paste that, toward the position value at K2 based on the percentage. So we're blending the position, and for rotation, we'll have to use Math Helper to do a linear interpolation. So the key 1 angle working toward the key 2 angle, and percent. Same concept with scale. Just copy this line and change it. Scale is the vector2 linear interpolation of the scale value towards the K2 scale value. And then the offsets for each vertex for doing warped animations. Same sort of thing as position here. So we copy and paste it. We'll say 01, 01 here, and 01 here. 02, 03, and 04, 2, 3, 4, and then just go in and change these to 2, 3, and 4, and over here too, 2, 3, 4. Okay, from that above data, we can get the final transformed vertices. So we'll start with x1 value. That's the upper left-hand vertex, using the model coordinate M1. So that's the offset from the center to the upper left-hand corner. We've got to scale it, do the same thing for the y coordinate, change this to y1, m1.y, scale.y. Copy this entire line, paste it 3 more times, change this to 2, 3, and 4. Same with the model, 2, 3, 4, y, 2, 3, and 4. And m.y be 2, 3, and 4. I'll just put some comments in here for a second. Okay, I unpaused it. You can take a look at the comments I added. So, as you may remember, in the MeoMotion class, I added these customizations for the animation properties, like adjusting the speed and adjusting the offset. So if the character animation of one of your animations isn't lined up correctly with the other ones, it is possible to do it in here and you don't have to do it in the editor. So we're going to add that offset factor in the Meow Player. So that's what I did right here. For the position of the sprite, well, actually this will be for the position of all the sprites because it's looping it. It's adding that offset factor. Let's deal now with the rotation. We're only going to do the calculations for the rotation if the rotation is not 0. First we'll get the cosine and sine value for the rotation based on the angle, ROT. Cast a float using math, cosine of rotation, and we'll have a sine variable, which is the same sort of thing. Okay, now that we got the angles, let's work out our final vertex coordinates after position and rotation. So vertex 1, the top left vertex, dot x will be the position dot x that we calculated for that sprite, plus, so the position is actually the center of the sprite, and then you have your modeled points around it, which we adjusted here by scaling them. So those are kind of like the vector offsets from the center. You could think of it like a radius. So x1 times cosine minus y1 times sine to get the first x coordinate. You may remember from the quad batch tutorials how these rotations work, so I'm not going to go over that again, but if you look in there you can see how that works. But it's basically just explaining how the rotation of coordinates are being done. For the y value, it would be x1 times sine plus y1 times cos. Alright, let's just copy this a few times. For vector 2, 3, and 4, using x2, 3, and 4, and y2, 3, and 4. Same here for the y value. Vertex 2, 3, and 4, x2, 3, and 4, and y2, 3, and 4. It looks okay. Okay, I just added this comment here that it is possible to add more advanced animation stuff to this for automatically trailing hair or tail or something like that. It can be done. So otherwise, we're just going to add the sprite position and the model coordinates together because there's no rotation. So we just have to add in this offset position to the model coordinates, which are modeled around 0 by default, to get each part into the correct position on screen. So I'm just going to pause it and add that real quick. So all I did here was sort of like up here, except there's no rotation. Just add the position x to the x1 model coordinate. That's the upper left hand offset. And then you got the upper right hand, lower right hand, and lower left hand offsets added into each vertex. Now we can add in the offsets, like the animated offsets that we animated in the original MeoMotion software for making distortions. So let's add to this vertex 01, the distortion offset, and then V2, 3, and 4, O2, 3, and 4. And to flip the character, it's actually easier than you think. So if we want to flip it horizontally, all we have to do for the final vertices is negate them. For the x values anyway, because we're only flipping horizontally. Oh, I made a mistake in explaining this up here. Position is not the position on the screen. Position is actually the position offset of the part relative to the root bone of the character. When it draws the transformed vertices and use what I call the scene origin, which is the position of that character on the screen, it won't be placed into the correct position on the screen until it calls draw transformed vertices and supplies the position. Okay, and that is it for the update. Now let's just make it so that it can draw the final rendered data to the screen. First thing we'll do is if not active, return int I equals 0 for index. We need a counter for the loop, so n equals 0. P for the part that will actually be shown if there's any part swapping. We'll say while n is less than part count. N++. Now we're not actually going to render them in the order of n to part count. What we're going to do is get the index of what we really want to render from final n order. So now we have the index of what we actually want to render. That way it draws them in the correct order so that the layers are layered properly. If it's supposed to hide it, then we'll just increase n and continue. So we'll skip the rest of this. Otherwise, we'll move on. Part to render is p. The alpha value of our color is going to be, and that's the alpha value of the color that's passed into the draw call. So we're going to cast it to byte, and what it will be is, it'll be the alpha value times 255 and 0f. So then that way the color or the tint that you want to render, its alpha channel, will be modified by the interpolated alpha value. And if pre-multiply alpha is true, then we have to say that the color is from non-pre-multiplied of the color dot to vector 4, and that'll convert it to a compatible alpha value. That'll convert the color so that the alpha value is pre-multiplied, so the red, green, and blue values will be reflected correctly. Otherwise, we'll just say the color is color. And there's not much to it, other than now we just have to say draw transformed vertices, which will take care of the rest. Use the source rectangle of the part we want to draw, the position, drawing at the position associated with the character, and that will adjust these final vertices so that they're relative to the player position. And supply the color. I'm just going to add some comments here. Okay. for our MeoPlayer, let us also make a method called getIndex, in which you can supply a string for the animation name, and that way you don't have to supply the character sheet because it already knows which character sheet is associated with this player. If animation name is currently none. So if this is an automated process and it asks what is the current index and the current animation name is set to none externally, this will just make sure that it returns 0. Chances are good this will never happen. You might not even need this line at all. So we're going to use the MeoMotion class to get the index, using the sheet name that's already set up for this MeoPlayer, the supplied animation name, and whether or not we want to show errors. So looking at that method in MeoMotion, there are lots of times you may want to look up an animation where the animation doesn't exist, in which case you just return 0, and you may not want it to do a console.writeLine animation not found in dictionary each time, so in which case you'd want to make sure show error messages is false. So you'd actually specify false when you call getIndex for that particular circumstance, because you know that there's going to be an error and you don't want it to be writing this. Anytime it writes console.writeLine, it's going to slow down the program. Something to keep in mind. So if your game starts slowing down, you might want to check to see if you have any console.writelines happening by checking your output box and seeing if it's writing anything there, because that could be what's happening. Okay, so I'm back in MeoPlayer, and that's it for the MeoPlayer class.